Hello everyone, welcome back to Tanisha's Concept Corner. So in physics we were doing the chapter ray optics and optical instruments. In the last class I did till this power of lens. So let us continue. So there is a question given over here. It says that if the focal length is 0.5 meter for a glass lens, then what will be the power? As we have already seen the formula, power is equal to 1 by focal length, and ensure that the focal length is in meter. And if this focal length is positive, you're going to get the power also as positive. That means it's a convex lens. So focal length is positive 2 diopters, the SI unit of power 1 by 0.5, that is plus 2. The next question, they're asking us the radius of curvature of the faces of double convex lens. They have given R1 and R2 for a double convex lens, and they have given the focal length. Focal length will be positive because it's a convex lens. Then they're asking the refractive index of the glass. So the formula that we have already derived in the previous class is over here, where 1 by f would be equal to refractive index minus 1, 1 by r1 minus 1 by r2. So we will be using this particular formula. So 1 by f, focal length was mentioned as 12 centimeter. We will take it positive because it's convex lens. Then refractive index is what they're asking in the question to find, minus 1, and both r1 and r2 values are also given to us over here. The radius of curvature 10 and 15 centimeters, but r2 should be considered as negative because over here we have seen r2 towards the left side. Generally this is how the convex lens is and how the refraction is taking place. So if you see, R2 is towards the left side, so we have to consider it as negative. So if we see, so all the values we know, focal length we know, R1 we know, R2, consider it as negative, then you can easily find the refractive index by just transposing and doing the normal arithmetic equations. Now the third question is, suppose the convex lens is, again convex lens, positive focal length is there, but in case of air, and what is the focal length in water? So there is this convex lens made up of this glass material, and if you're going to hold up in air, then this is the focal length that it's going to have. But if you're going to put it inside the water, then what will be its focal length? Again same formula only we will be using. So first take this glass and air interface. So in the glass and air interface, they've already given the refractive index of glass over here, 1.5. So if it is air glass interface, refractive index will be taken as 1.5. So in place of n, put 1.5, then minus 1, you got 0.5. And they have already given the focal length, that is 20. R1 and R2 values they didn't give, so just put it like that. Now, they're asking us in case of water surface. So it is water and glass now because convex lens is glass. So water and glass surface, we will have the values, but the thing is that we don't know the refractive index for it because they didn't directly give in the question what is the water glass. They have given air and water, air and glass, but what about water glass? We will use these refractive index values only to get whatever required is there to substitute in case of glass and water interface. So let us see how we will do that. So we know the formula for this refractive index. We need refractive index for water and glass. So generally general formula is like this, NW by NG. But now we don't know the values. How will we actually write it? It's simply, we will write like this. For air and glass interface divided by water and air interface. Why am I writing like this? So first take only the numerator and see. Air and glass, what will it be equal to? Na divided by Ng. See, generally N21 is there, meaning it is N2 by N1. This is a general formula. Now if NWA is there, it's in the denominator. So if it's in the denominator, NW by NA, we will take the reciprocal of this. Then what will you get? NA divided by NG into NA divided by NW. So we are not getting the value that we need over here, so we will just interchange this. So you can always cross check like this. To interchange, you can interchange it with in this way. Now we will get the desired value. So instead of W over here, put A by W. So NAW will be NA by NW. Now you will interchange it as you get it to the numerator. Then it will be NW divided by NA. This NA and NA will get cancelled and you will get NW by NG. So we will consider this one. We know the values because glass and air they have given over here. For glass and air, the refractive index is 1.5. Then in the denominator we have for air and water, we have 1.33. So we can simply substitute in the, here there was no problem because it was glass and air interface and we know the refractive index for glass and air interface 1.5 that was given in the question. Now we are taking it for water and glass. So that's what we derived over here. We took it for air and glass and air and water. So this is 1.5 divided by 1.3. That is what you will take over here. So if you take 1 by F, the formula that is there, it is actually 1 by F is equal to N value is nothing but 1.5 divided by 1.3 minus 1 because it was N minus 1, and then it is 1 by R1 minus 1 by R2. We don't know the values for the radius of curvature. So we will just put it in that way only. So now they have just rearranged it. 1.5, if you take the LCM over here, cross multiply 1.5 minus 1.3 divided by 1.3. Send this over this way. So you will simply get 1.3 because this is in the denominator. After going over here, it is going to become multiplication. So 1.3 into 1 by F is this. This one only I have sent here. So this will be as it is. That's what they have written over here. 1.3 by F, 1.5 minus 1.3 and 1 by R1 minus 1 by R2 as it is. Now we will just, these two equations are there, divide it. If you divide, this and this will get cancelled. So that is why there is no need to find out R1 and R2 only. That's why they didn't even give the values, because you can simply divide these both equations and you can cut them off. And these both 1 by 20 by 1.33 divided by F, 0.5 is known, 1.5 minus 1.33 is known, only unknown value is F. So if you divide and then you equate it accordingly, you will be able to get the F value, that is positive 78.2 centimeters. This is how you come at the equations. General calculations you guys can do it. Now for one lens you have seen how the power is and how everything is, but what if the two lenses are combined together? So that is what they are saying. Suppose take lens A, lens B. Now focal length for A will be f1, for B it will be f2. They are in contact. Let the object be placed point O somewhere beyond this focus. Then the first lens will give an image I1. Now I1 is actually a real image. Generally guys, if there is a lens and right side the image is forming, that will be real image. Left side if it is forming, that will be virtual image. So for real images, because it's right side, you will take it as positive distance. At left, because it's virtual image, for virtual images you take it as negative. Why I am saying this? Because in lenses this is the case, but in mirrors it's exact opposite. In mirrors, right side virtual image used to form, real image used to form left side. So whenever we have to take the distance for real image, we used to take it as negative. So in lenses it is just the opposite. So that's why I'm saying this. Now I1 towards the right is a real image. Now it will act like a virtual object for the second lens, because second lens also needs the rays. We have seen in our derivations also how from the object the light rays pass through the first lens is forming one image, then that is acting like a virtual object for the second lens, then final image will be formed. So final image I will be formed. we must keep in mind that formation of image by first lens is like only presumed to facilitate the determination of the position of final image. We are only drawing this to to know where exactly the final image is being formed. But generally, directly this image will be formed. You won't be able to see two particular images when you're keeping two lenses together. This is just we are drawing for our sake to know where the final image is forming. So while directing the rays that are coming, first lens gets modified in accordance with the angle where it is striking the second lens. So this both will act hand in hand. So if the light is coming like this with this angle itself, it will change and already it will form over here only. It's not like first this is forming, you'll be able to see this image. Practically, if you think about it, this is just for our purpose we are drawing. Now let us see. We know the lens formula, 1 by f is equal to 1 by v minus 1 by u. For first lens, let us think. For A lens, we have already said for A lens, focal length is f1, and over here, image is forming at v1, object distance is u. So 1 by v minus 1 by u, we are writing 1 by v1 because their image is being formed. Now for second lens B, 1 by v minus 1 by u is equal to 1 by f, that formula only, but focal length for the second lens is f2, that's why we have substituted f2. And where is the image being formed? The image is being formed at V. This is the image formed by the second lens. So 1 by V minus not 1 by U, 1 by V1. Why? Because V1 is actually what? I1's distance. I1 is acting like the object for the second lens. You won't consider this object now. So take V1 as your object distance. 1 by V minus 1 by V1 is equal to 1 by F2. Now simply add these both. 1 by V1 is positive here, 1 by V1 is negative here. This will get subtracted and it will be 0. Now 1 by V is positive, minus 1 by U is left out. You are adding both the equations, so 1 by F1 plus 1 by F2. Now we already know according to lens formula what is 1 by V minus 1 by U. It is just 1 by F. So left hand side, okay, 1 by V minus 1 by U, here they have wrote it as 1 by F. So left hand side, you just have to substitute this value as 1 by f, and right hand side will remain the same, that is 1 by f1 plus 1 by f2. So we have just derived this formula whenever there are many lenses suppose in contact together and you need to know their combined focal length, their power. So what do? You simply add all the inverses. Now many students might make a silly mistake. They might not keep this formula in their head, and when the question comes like, okay, there is one lens with 10 focal length, the other one is with 20 total, meaning they will directly add of 20 and 30. Take the inverse, 1 by 20 plus 1 by 30. Keep this though this formula is really simple, but keep this in mind. Alright, and we already know if you take the inverse of this focal length 1 by f, meaning simply it is power. So P1, P2, P3 like that. If power is there, not an issue. If they are giving power of one lens, power of second lens, you can directly add the powers. But if they are giving focal length, take 1 by f1 plus 1 by f2. In this way you have to take. So just like 1 by f1 plus 1 by f2 we have added here, if many lenses are kept together, then you have to simply add their focal lengths in this way. Now for power, one thing again you have to keep in mind is that it may be positive or it may be negative. For convex it is positive, for concave it is negative. So keep that in mind and then add. Signs should be important. Just because plus is written, don't leave the signs of this convex and concave lens. So in that way you will be able to get the total power. And combination of lenses, they are generally helping us to get whatever magnification we need. Like many optical instruments are there, microscopes, telescopes, we are using them to magnify the objects that we are unable to see properly normally with naked eye. So if we have to magnify, according to that we are combining the lenses. And also it enhances the sharpness of the image. Now since the image is formed by the first lens and then becomes the object for the second, if you want to get the magnification, just do the product. So when combined lenses are given, for focal length take 1 by in inverse way and then add. If they ask power, directly add, but keep in mind if it is convex then positive, if it's concave then negative. If magnifications, multiply all the magnifications, because magnification is like ratio, right? How much the image has become more larger as compared to the object. So here whatever image the first lens is forming, that is itself becoming the object for the second lens. So because of this ratios, we will simply multiply all the magnifications to get the final magnification. Now here one more question is given to us. Here generally by shape itself you should be able to recognize that this is a convex lens and this is a concave lens and this is a convex lens. But in case if you are not able to see the focal length, positive meaning convex, negative meaning concave, and they have given distances over here, they're asking find the position of the image formed by the lenses combination. Where will this final image be formed? That position, how much distance I have to find out. So same thing, we will apply lens formula. 1 by f is equal to 1 by v minus 1 by u. So for first lens, we are writing f1 v1 u1. v1 we don't know where the image is forming by the first lens. And u1, it's 30 centimeters where the object is placed, that is given. And because it's towards left and the object distance generally should be taken as negative, you will take it as negative according to the sign convention. And focal length, because it's convex lens, you will consider it positive. In exam they might not give this signs, so keep in mind this is a convex lens meaning positive focal length. Then we got, by interchanging this, taking LCM, we can get v1 as 15 centimeter. Now okay, this lens image is being formed, but that again will act like an object for this lens. So for this lens, the object distance is nothing but the image where it is formed by the first lens. But don't directly take 15 centimeter. You have to take 15 minus 5. Why is that so? Because if this image is whatever this lens, the image is forming, suppose over here, then that is acting like an object, gets reflected, and finally the second lens is forming image somewhere over here. For getting that v1, which is 15 centimeter, we generally measure from the center. Because this is for first lens, we are measuring from the center of the first lens. Okay, that will make sense. But for second lens, if I want that object distance, I have to measure from the center of this lens, not the center of this lens. So if I want only from the center of this lens, I have to remove whatever this distance is there, and they have easily given this distance is 5. So simply subtract the 5, you get 10. Now that is nothing but the object distance for this. So 1 by v2, for the second lens it is v2 minus the object distance will become 10 centimeter, basically the image formed by the first lens, and they have given the focal length as negative 10. This is concave, so focal length will be negative. Now if you see, if you send the 1 by 10, it is negative 1 by 10. If you send it over here, it becomes positive 1 by 10. Positive negative will get cancelled, you will get 0. If 1 by v2 is 0, if 1 by v2 is 0, what will be v2? You will take the inverse, because this is inverse. Take the inverse of this, you will get v2. Take the inverse of 0. 0 is in denominator, so you have to get infinity. So that is what they have given, infinity. Now for third lens again, this will become the object distance. Now no need to worry what to subtract, what to add, because whatever you add or subtract or do anything with infinity, it is going to remain infinity only. So v3, where this final image is formed, you don't know. The object will become object distance is basically this image formed by the second lens, and focal length is again given 30 centimeters positive, because it is again convex lens. 1 by infinity can be simply considered as 0 itself. So 1 by v3 is 1 by 30. Take the inverse of v3. It is basically 30 centimeters. So where is the final image formed? 30 centimeters to the right of the third lens. So please understand the derivations properly so that you can use it in the numericals as well. Only if you would have understood how this formula came in this manner, how that image is becoming the object for the second lens, like that, if you're able to understand, then numericals also it will be easier to solve. Now let us proceed. Now it is refraction through a prism. We have seen spherical surface, we have seen normal plane surface. Now let us see if it is through a prism. Angle of incidence is there, it is bending towards the normal, then away from the normal, you're drawing the normal. Now between the incident ray and normal, you will get I, that is angle of incidence. Between the normal and the refracted one, you will get angle of refraction. Same over here also. Here it is emergence, because it is emerging out. And if you are just going to track these emergent and the incident rays back, you will get something as del. This is deviation. That is what mainly we are going to find out in this derivation, angle of deviation. So if we see over here, this is a quadrilateral that they have given, AQNR. AQNR. So this is the quadrilateral and they're saying angle A plus angle QNR is 180. In quadrilateral, it's generally 360 degrees, the total one, if you add all the angles. So if you see over here, this is a normal. So if this is normal, this will be 90 degree. This is also normal, this will be 90 degree, the entire angle. 90 plus 90 is 180. Now how much more? This angle and this angle is still left. To make it 360, how much more angle is needed? 180. So here 90 plus 90, already 180 is there. So that obviously means angle A plus, this is angle Q. Angle Q, if you add, you have to get 180. Then only all the angles, if you add in a quadrilateral, you'll get 360. So that is what they have written over here. Angle A plus angle Q and R is 180 degree. Now if you see, for angle A, what they have done, they have considered the triangle QNR. If you consider triangle QNR, again what is happening? R1 angle is there, R2 angle is there, QNR angle is there, it will be 180 because all the angles in a triangle should give 180 degrees. Now compare these both. QNR is common, 180 is common, only thing that replaced angle A is R1 plus R2. That means this R1 plus R2 should be equal to angle A. That is what they have written over here. Now finally, to get this del angle, what they have done, you can think this as an exterior angle for this triangle, the upper triangle. Instead of QNR, look at the upper triangle. If this is an exterior angle, generally you can add these two interior angles and get this. So to get that only, what we are doing, because we don't know those angles, I minus R1 we can do. If you see over here, just look at this path. If the incident ray would not have deviated in this way, it would have just gone like this. Then consider this entire angle, that also would have been I, vertically opposite. This entire thing is I, but this is R1. From entire I, if you remove R1, I'll get this angle inside this triangle. Same thing. If this would have just passed in this way, without getting deviated, this entire angle will be E. Vertically opposite angles. E is there, but R2, if you subtract from the entire angle, if you subtract R2, I'll get this angle. If I add these both, I'll get this deviation. So that is what we have done over here. I minus R1, E minus R2, add them both. Now what will you get? I plus E, both of them are positive, minus A, because minus R1 minus R2 is written there. Minus R1 minus R2. Take minus common out, you will get R1 plus R2. You already know what is R1 plus R2, that is A. So that's why it's minus A. R1 plus R2 is A, so that's why it's minus A. This is how you will find the angle of deviation. So angle of deviation is readily depending upon the angle of incidence, and generally for this angle of incidence, angle of emergence, both of them will be associated. But in a case where I is equal to E, then two values you can take it in the same way. Like you can take it as 2I, because I is equal to E, both can be considered as I, you can write it as 2I. And it will remain the same if I and E are interchanged, if I is equal to E. Now, minimum deviation, whenever this minimum deviation happens, whatever refracted ray that is there, it's getting refracted, it will be parallel to the base of the prism for minimum deviation. When will that occur? If I is equal to E. Deviation will become minimum deviation if I is equal to E. In such a scenario, R1 will be equal to R2. It is obvious. See, if I is equal to E, that means the ray is coming from outside. So it's inside the prism, meaning its direction will change. It will bend by some angle, that is R1. Okay. Now if it is going out by same angle as I, here bending also should be same. Otherwise, how will it go same angle as I towards the out? That means R2 should be same as R1. Inside, bending by both these rays should be same. Then only exteriorly the angles will be same. So that is what is happening over here. So when R1 is equal to R2, we know A is what? R1 plus R2. R1 can be considered as R, because if all the values are equal, why two variables we need? Simply consider it as R. R plus R will be 2R is equal to A. R will be A upon 2. Here you already know, right? R1 plus R2 is A. You will use two different variables like 1 and 2 only when they are different. If they are same, simply write 2R or 2X, anything. Then same way for the deviation formula also 2i, as I said already over here. If I is equal to e, consider both of them as I only, because you'll use two different variables only if the values are different. If they're same, use same variable I and I. So I plus I will become 2i minus a. Now simply send a towards that side, it will become plus. So a plus dm, and I will be here. If you send by 2, because here it's in multiplication, send to the left side, it will become by 2. You got the I value, you got the R value. Now what are you trying to do? Refractive index of the prism. N2 N2 by N1. What is this Nels now? Sin I divided by sin R. You know what is sin I? Same thing. A plus dm by 2. You know what is sin R? A by 2. Now if they are going to ask the refractive index, generally while doing the experiment we can know A is nothing but this angle of prism. Generally if it's equilateral you will get 60 degree. So whenever they give you prism, okay, you will measure this angle and you will be able to measure the deviation, and then you can find the refractive index. Now for more smaller angles, you know sin theta can be approximated as only theta. No need to write sin for smaller angles. So again, just take these inside values, no need to consider sign. Then a plus dm by 2 by a by 2, take the reciprocal, you will get 2 a upon 2. So you will be able to cancel off this 2, then you will transpose and find it like this. If you want to see, we will write it in this way. So it was a plus dm by 2 by a by 2. So by a by 2. If you take the reciprocal, it will become a plus dm by 2 into 2 upon a. You can cancel this 2 and 2 off. So what will you get now? This was the formula for the refractive index of the prism is equal to, now see, a plus dm by a, meaning I can separate it. A by a is 1 plus dm by a. I can write in this way. I need the minimum deviation, so send this 1 over here. It will be n2 1 minus 1. This is in division. If it goes there, it will become multiplication. That is what they have given for the minimum deviation formula. Now let us look through optical instruments. As we have said, now whatever all the things we have learned, the reflection, the refraction, lenses, mirrors, everything combined together, we have designed various instruments, periscope, binoculars, telescopes, microscopes, everything we have been using. The most natural one that we have is our own eye, and we already know how that works, how it is forming image on retina, what kind of lens, how converging is happening, everything we studied in 10th grade. So let us now in detail study about microscope and telescope. So let us see about a normal simple microscope in the first scenario. So you can call it a simple magnifier. It is a converging lens, meaning convex lens. Now it will be of small focal length. Now in order to use such a lens as a microscope, generally lens will be put near the object, generally one focal length away or less than that. At the principal focus you can put the image, then at infinity at the focus you can place the object, then at infinity image will form, or less than that. If you are going to keep it, it will form less than infinity. Here if you see correctly, at principal focus if you are going to keep, where the distance is focal length, we know if the object is at focus it will form the image at infinity. But sometimes you can keep it way less than that, then image will form nearer, less than infinity. So both the scenarios are fine. Now what is our main requirement? That is most important. We want to get erect, magnified, virtual image so that we'll be able to see the object clearly. And generally, if you want to comfortably view any object, we know least distance of distinct vision 25 centimeters should be near, or till infinity our eyes can see without any strain, without having it blurred, you will be able to see. Now take any book and keep it very near towards your eyes, like less than 25 centimeters, you won't be able to read it. It will be completely blurred. And if it is more away distance, if you're not having any power like myopia, you can see it clearly. Now, if the object is at a distance focal length, then the image will form at infinity. If it is slightly less than focal length, then image will be closer than infinity. That's what I've already said. Now, for comfortable viewing, generally 25 centimeter to infinity. But again, if it is 25 centimeters and it is nearby, it will cause some strain on the eye. If the object is nearby, the rays should converge more and it is straining the muscles in our eye. So generally, if you want to view it more comfortably, it is better that we keep the object in such a way that image is forming at infinity, meaning at correctly at principal focus if we keep the object, and properly if we place our eye. Now, what are we going to derive over here? We are going to derive the magnification, because that is what is main thing. We want to magnify whatever object we are having to view it properly. So see this images over here. First scenario, it is not at principal focus, it's somewhere little nearby, so the image is forming. Again, when it comes to lens, if it is forming image at left side, it is virtual. It will be virtual, it will be some amount of magnified, and you will be able to see at a particular point, near point, least distance of distinct vision, basically 25 centimeter or more farther than that. This theta naught or theta O is how much angle that image is forming at your eye. That is what is theta naught. Now this distance is least distance of distinct vision, so we are thinking it is forming correctly at 25 centimeters. In that way we have placed the object, and object's height is h. Image height is h because image is forming at the 25 centimeter. Now in second scenario, what is happening? We are going to place the object towards the principal focus so that the image will form at infinity. If image is forming at infinity, what will happen? This theta I means what is the angle that image is creating in our eye. This will be equal, so this is how the angle is creating at the eye, that is theta I. So now let us derive. So we know magnification will be V upon U. So let me write it in this way now. Magnification equals V upon U, but V upon U meaning I can write it as V into 1 upon U. Then what will 1 upon U be equal to? It will be equal to M by V is equal to 1 upon U. Now normal lens formula you take. What is it? 1 by F is equal to 1 by V minus 1 by U. So I will send 1 by U this side and send 1 by F this way. Then what will happen? 1 by U will become positive. I'm gonna get 1 by V minus 1 upon F. Then we already know the 1 by U value, that is M by V. So substitute. M by V is equal to 1 by V minus 1 by F. Only magnification we need, right? So send the V that way. Then what will you get? M is equal to, this is in division, if it goes towards the right, it will become multiplication. 1 by V minus 1 by F. Now multiply inside the bracket. Then we will get magnification is equal to V into 1 by V. V and V will get cancelled, 1. Then minus V into 1 by F will become V upon F. Now this is a scenario where I am saying, suppose the image is formed at 25 centimeters. So that least distance of distinct vision, you generally represent it with D. Generally if you're seeing D, you have to know that it is 25 centimeters. That is what they're going to talk about. Now because it's towards the left, it is virtual image, meaning sign convention, negative D you have to consider. Instead of writing negative 25 centimeters, I'm writing it as negative D. That is the image distance. So how can I write? M is equal to 1 plus, because minus minus is plus, D upon F. This is the magnification. Now What if the image is at infinity? Okay, if image is at d at 25 centimeters, we have given in this way. If image is at infinity, we will do one more way of derivation. So we know that magnification is equal to h dash upon h, the general formula that we know. Similarly, we can use one more formula saying that theta I upon theta naught. Angle formed by the image at I and angle formed by the object at I. This also, if you take the ratio, you will be able to get magnification. Now let me take tan theta O in case for the object. Refer to this image over here. What is tan theta? Opposite by adjacent. So it's going to be h upon d. It is going to be h upon d. So you can think it as h upon negative v also, because it's about the image distance. Now h dash upon h is also equal to what? It is also equal to v upon u. Equate in such a way that you get only h dash value. H dash value you have to get, meaning send this denominator to the right side because it's a division. If you send it towards the right side, it will become multiplication. H dash will become as vh upon u. Alright, now what will happen? Just like here, tan theta naught you got. Similarly, tan theta I, what are you going to get? Instead of h, just put h dash. H dash is height of that image. By negative v you will get. What is h dash value? Substitute. vh upon u divided by negative v. Meaning I can simply write like this. Divided by negative v. This v will get cancelled. You will get negative h upon u. In this scenario, u, meaning where the object is exactly, it is placed at principal focus, because then only you will get the image at infinity. If you see here, for focal length we have pointed in the left side itself. That means f is negative. So instead of u, write f, because that is where object is placed, but keeping in mind the sign convention. So negative will get cancelled. We'll get h upon v, h upon f. Now why are we doing all this? To get the magnification. What was the magnification's formula? Just like h dash upon h, I told theta I upon theta naught we can do. So let us do that. You can just write one step saying that these are the smaller angles. So tan theta naught can be approximated as theta naught. Tan theta I can be approximated as theta I. So that is what we are going to do over here. Theta I value we got as h upon f. Theta naught value, take this value only. Don't take h upon minus v, take this value. Now what is theta I upon theta naught? H upon f divided by, so simply take the reciprocal, d upon h. H and h will get cancelled. Finally, you will get the magnification as d upon f. In case if the image is forming at infinity. So this was the derivation given over here. For at 25 centimeters, it is 1 plus d by f. And then finally for infinity, we have taken, because we are considering the angles over here, call it as angular magnification, d upon f. Now if you look at the 25 centimeter where the least distance of distinction is there, generally we are placing the object over there so that we will be able to see it comfortably. But this lens will allow us to bring it way more closer and still be able to magnify it so that we can still see it clearly. That is one point written over here. Now if you compare, when it is at least distance of distinction, the magnification was 1 plus d by f. But for infinity, the angular magnification is d upon f. That means 1 extra is there for the 25 centimeter ones. So the 25 centimeter ones, if you're considering it, magnification will be more, but it is not very comfortable at viewing, because at infinity only it is really comfortable at viewing. So one thing has one disadvantage, you can say. There you cannot comfortably view, but magnification is more because 1 plus d by f is written. and over here magnification is slightly less, but you can it will be more comfortable, and the difference in magnification will be generally small, not too much difference will be there. Now we shall assume the image at infinity. Okay, now if we are going to consider this compound microscope, there is another set of derivation to do. We have considered a single microscope now, so that we will cover it in the next class. So about the compound microscope, and we have telescope. After this the chapter will be done. So if you like my way of teaching, please like this video, and if you have any problems and any doubts, please feel free to leave a comment in the comment section, and please subscribe guys. See you in the next video. Bye.